Hello, everybody. Today, we'll talk about a new topic, is the theory of NP completeness. Hard problems. The boss said to its employees, what you can say, I can't find an efficient algorithm, but neither can all these famous people. So, hard problems, they do not have efficient algorithm to be solved. Okay? So, first we'll talk about the complexity class P. It's deterministic in nature, solved by conventional computers in polynomial time. Like complexity of 1 is constant, log n sublinear, log n linear or polynomial, n log n nearly linear, n square quadratic, and so on. So the polynomial upper and lower bound. So every algorithm, every problem has lower and upper bound polynomial. Complexity is polynomial, so it's called P problem. P problem means deterministic. Polynomial time can be solved by polynomial time and by conventional computer. Non-deterministic algorithms consist of phase 1, guessing, will guess our solution. Non-deterministic algorithms has no solution in polynomial time. So we'll guess our solution and checking or verification. So we guess our solution, we assume our solution, then we're checking in like polynomial algorithms. So if the checking stage of a non-deterministic algorithm is of polynomial time complexity, then this algorithm is called NP algorithm. So NP is non-deterministic polynomial algorithm. So P is polynomial, is deterministic polynomial algorithm. NP is non-deterministic polynomial algorithm. We will solve it by guessing. We guess our solution, we assume our solution, and checking for that solution in polynomial algorithm. Example, NP problems. Example, we have lot of NP problems. Searching, MST, minimum spanning tree. Sorting, satisfiability problem SAT, satisfy. Satisfiability means satisfy. Okay, problem SAT. Traveling salesman or salesperson problem, TSP, and other. Okay. These algorithms or these problems are NP problems. They have solution, they have non-deterministic polynomial solution. So in general, we have this relation between P and P and NP hard and NPC. So P, the class of problems which can be solved by a deterministic polynomial algorithm. This is P. P is subset of NP. P is subset of NP. So NP, the class of decision problem. Decision problem. Focus on this word. Decision problem or guessing problem, which can be solved by a non-deterministic polynomial algorithm. Here, P is subset of NP. Now, NP hard, so the class of problems to which every NP problem reduces, which is mean limitation. So This, if we have problem in NP hard, or if we have problem, we'll call it NP hard if we don't have solution on it, but we have solution reduced to NP, means go to NP solution. So if we have similar problem, has solution in NP, okay, so we can reduce X solution, X problem to NP reduce. Reduce يعني نقربه عليه, نقربه close to another similar problem has solution. So this is called NP hard. NP complete or NPC, the class of problems which are at the same time NP hard, no solution, but reduce limitation to another solution, reduce to another solution, and belongs to NP. Belongs to NP means decision problem. Decision problem. So the solution of NPC will be guessing plus reduce at the same time. We guess the solution and reduce the solution. Two methods to get NP complete, NPC. Okay. All of this, NP, NP hard, NP complete, all are NP. So we call it NP, non-deterministic solution. P is polynomial, deterministic polynomial solution or algorithm. Others, NP, NP hard, NP complete, are non-deterministic polynomial algorithm. So we have some concept of NPC, non-polynomial completeness. In reduction, what is mean reduction? If we call problem A reduces to problem B, means A infinity B, or limitation B, or goes to B, okay, or close to B. So problem A reduces to problem B if and only if A can be solved by a deterministic polynomial time algorithm using another deterministic algorithm that solves B in polynomial time. So again, problem B has a deterministic algorithm. Problem B has deterministic algorithm. If you want to solve problem A, we don't have the solution of problem A. We want to solve problem A. So if A reduces to B, if A reduces to problem B, then A has solution. Means if we can use the method or the deterministic algorithm polynomial time in B, use it in problem A, and has finite or deterministic value or result, so we can call A is reduced to problem B. Okay? We'll see examples later. It does not seem to have any polynomial time algorithm to solve NPC problem. So NPC problem, approximately non-deterministic algorithm, approximately polynomial time, approximately, because we use reduce. Verification means here verification. The theory of NP completeness always considers the worst case, not NP completeness. All algorithms always consider the worst case algorithm, the complexity of the worst case. Always use worst case complexity for all our algorithms, NP or P. So now we'll talk about decision problems. The solution is very simple. The decision problems, the output will be yes or no, true or false. So it's a decision problem. Optimization problem are more difficult. Example, the traveling salesperson problem, TSP. If we want to use optimization version, find the shortest tour between the cities. Travel salesperson will visit every cities, okay? So find the shortest tour to visit all the cities. If this is optimization version, it's very hard. Whereas decision version, is there a tour whose total length is less than or equal to a constancy? So when we convert our algorithm or our solution or our given to another question, so this decision version is very easy than optimization version. So here we'll solve the SP optimization problem by decision algorithm. So we'll calculate the complexity or capacities 1 and test. The second pass, the third pass, the n pass. Then we can find the smallest CI between them. So this is decision algorithm. We decide each one is the shortest. This is better solution than optimization without decision. Okay? Example here. This is the traveling salesman problem, TSP. Later we'll see its algorithm. This is from subset to from Hamiltonian path. Hamiltonian path, okay, is we have network. We want to visit every node one time. We want to visit all nodes by visiting every node only one time. This is Hamiltonian path. So the example of Hamiltonian path will be traveling salesman problem, which is we have integer cost between each two cities. This node represents cities. The salesperson wants to make a minimum cost circuit or network, visiting each city exactly once, no return, no return. Okay, if we review digester algorithm or Kruskal algorithm or Prime's algorithm, all this algorithm, we have return. We have digester algorithm, we have visited each node twice or thrice to calculate. So digester algorithm, we cannot solve Hamiltonian path or travel salesman person. So, okay, later we'll see which algorithm in the next lecture. Okay, so we want to visit every cities once and return to initial start. So we have return tour. So this is NP problem. This is NP problem. So we assume some matrix to solve it. Okay, this is NP problems. One of NP problems. Now, the other example of NP problems are the satisfiability problem set or satisfaction problem set. Example, the logical formula x1 or x2 or x3 and minus x1 means opposite of x1 bar and minus x2 امتى بتكون true? What are the values of x1, x2, x3 to get this equation or formula true? Satisfaction, verification, it's true. If we assign x1 is false, x2 is false, x3 is true. So false or true give us the first term here, give us a true. And because x1 false, not x1 is true. So this second term is true. The same for x2. x2 false, so not x2 minus x2 means not x2, x2 bar. So will be true and true and true. So the total formula, the whole formula is true. That's called SAT. That's called SAT, satisfaction problem. Okay, that's SAT. Okay, if there is at least one assignment which satisfies a formula, then we say that this formula is satisfiable. Otherwise, it is unsatisfiable. Example here, an unsatisfiable formula, it gives always false for all combination of x and y, for all combinations of x and y, or x1, x2, this equation always false, always false. Okay? If we take 0, 0, false, 0, 0, false. Okay? So 0, 1, this is false. Okay? This is 0. The second term is false. So all is false. 1, 0, the same. 1, 1, the last term is false. So this combination, this equation or formula is always false, whatever the values of x1, x2. So we call it unsatisfiable formula, because always is false, whatever the value of x1, x2. Okay? So, in summary, in this topic, certificates. We call it certificates if returning true. So the same, I will repeat, but in different way. Returning true. In order to show that the solution can be made, we only have to show only one solution that works. This is called a certificate. So we only have to show only one, or at least one, only one solution that works, that has true. So this is called certificate. That's how NP is working. If you have only one method or one way or one iteration or one solution to get close to polynomial deterministic time, so it's NP. We have solution, approximate solution. So returning false, in order to show that the solution cannot be made or the problem cannot be made, we must test all solutions. So false must be like before here. It must be for all combinations of x1, x2, all combination give us false, means unsatisfiable. At least one means satisfiable or certificate, the same. It's the same definitions. Okay? Okay? Any question in this topic, in this subtopic in this lecture? It's clear? Good.
Yes.
Good. Now, Cook's theorem. Cook's theorem said, if we have NP equal P, close to P, reduced to P, if and only if the satisfiability problem is a P problem. So SAT is NP complete. It is the first NP complete problem. Every NP problem reduces to SAT. So the solution of SAT, okay, Cook's solve it. So every NP problems, if we can reduce it to the same solution of SAT, we can solve it. We can get an answer. Okay, we'll see a lot of examples of that. Some NP examples. If we have circuit satisfiability SAT in the circuit, okay, we have logic gates, not or and. We have this circuit or Boolean algebra, like before. Take a Boolean circuit with a single output node and ask whether there is an assignment, at least one assignment of values to the circuit's input to give us output is true or 1. This is our satisfaction. So yes, we have 0, 1, 1, 0, 1, 0, 1, 0, 1 here, give us these values. So in the last AND, we have inputs 1 and 1, give us 1. So we found at least one solution, the output will be 1. So this is called SAT, by circuit or by Boolean algebra. Okay? This is called SAT. Another example, NP examples, is Knapsack, as you did it before in our lab. Knapsack, here it's another assumption. If we have given S and W, the weight, can we translate a subset of rectangle here to have their button edge on L, هنصفهم حد بعضهم, so that the total area of the rectangle touching L at least has weight W. So we select 3 maximum weight here, or 5 maximum widths, okay, to get W. So it's NP problem. Okay, we solve an example in lab before. It's NP problem. As you can see, the solution of this algorithm, Knapsack algorithm, as you can see, 0-1 Knapsack algorithm, as you can see, it's very hard. As you remember, we have 2 algorithms to solve it. So it's not easy. It's very hard because it's NP problem. The solution will be hard. As you can see, the solution is not always optimal. Okay, it's approximate solution. Also, we have a problem called vertex cover, VC. Given a graph and an integer k, the question is there a collection of k vertex, collection of nodes, such that each edge is connected to one of the vertices in the collection? Okay, so if we have, this is NP problem, vertex cover. The question is, we have this network. If we select A, B, D, F, if we select this, okay, has vertex cover or no? If we have each edge is connected to one of the vertices in the collection. Our collection here will be A, B, D, F. Every edge is inside it, so yes. We have remaining C, A, yes. So this edge, CA, is inside or touching, connected to the collection. EF, yes. So every nodes are covered. This is called vertex cover. We don't care the edge between C and E. We don't care about this. We care about these nodes must be connected to external nodes. So if yes, so these nodes are called vertex cover. So if we have these nodes, so we have cover all the network, because A connected to C, F connected to F. So this edge is connected to our collection. This edge is connected to our collection. So yes, we have VC here. Another example here, CE, as you can see, CE is connected to each other nodes. So if we choose only 2 nodes here, 2 vertex here, CE, yes, it's vertex cover. Only 2 nodes, but we can go from CB, from CD, from CF, also ED, EB, EA. So If we choose only 2 nodes here, we can go to all, we can cover all the vertex. That's why call it vertex cover. So in this network, yes, CE is vertex cover to connect to others. In this network, these 4 nodes are vertex cover. Okay? Later we'll see how the algorithm will work. Okay, today we'll finish. Later we'll see an examples and real algorithm how to solve these problems. Vertex cover, knapsack in another way, if we have time, SAT, and travel sales problem. Okay? Okay? And we'll want to solve that in our next lecture. How to solve Hamiltonian path or traveling salesman problem. Okay? Any question for this introduction to NP lecture? This is introduction to NP lectures. Any questions? Good. So I will stop the recording.